Hello, everyone. Thank you for joining us today. We are excited to have you here for our webinar, Multi-Body Dynamics Technology Leading the Defense Industry. Today, we'll look at how dynamic analysis is shaping the defense sector. You will see real examples from mechanical mechanisms, unmanned systems, vehicles, tanks, and even aerospace applications. We'll also talk about how using dynamic analysis early in the design process can make systems more durable, reliable, and cost-effective, especially under tough battlefield conditions. If you have any questions during the session, just type them into the Q&A panel. I'll be happy to answer them. At Function Bay, we are committed to sharing the latest NCAE simulation to support your work and research. Let's get started. Hello everyone. Today's webinar is focused on multi-body dynamics technology leading the defense industry. We will learn about various applications of dynamics analysis, particularly highlighting case studies from the defense sector. First, I'll briefly explain the concept of basic dynamic analysis through examples of past and present essential weapons. Following that, I'll explain how dynamic analysis is being used and can be used in the defense industry, focusing on the cases listed here. The clips are various examples of dynamic analysis technologies applied to the defense industry. As we explore different sectors, you will see applications ranging from traditional mechanical mechanisms such as rifles and robots to unmanned systems such as drones and missiles, vehicles and tanks operating off-road, and even aerospace mechanisms. This technology spans nearly every industry in this defense sector. Therefore, noise and vibration, system stability, durability, development cost, and time reduction are required in mechanical mechanism designs. In particular, since it is operated in a special usage environment battlefield, design for system durability and accurate operation is very crucial. By applying dynamic analysis to the design stage, it is possible to identify the dynamic load applied to the system in various environments in which it is operated and evaluate the deformation and durability of parts that may occur due to this. Furthermore, this approach helps prevent potential mechanism malfunctions or control algorithm errors, ensuring optimal performance under combat situations. Dynamics is a study of the relationship between motion and forces. It describes how an object's position, orientation, velocity, and accelerations are interrelated with the forces acting upon it, helping us understand how the object moves in space. Multi-body dynamics deals with the dynamics of systems composed of multiple interconnected bodies. Conducting a multi-body dynamics analysis involves applying dynamic equations to a mechanical system to numerically analyze how the system will operate. Modern multi-body dynamics analysis allows you to represent the 3D geometry of a mechanically designed system on a computer. Using an analysis program equipped with dynamics analysis capabilities, we can model, analyze, and evaluate the system. The video below shows the results of applying fundamental dynamics analysis to an automobile's clutch and pedal system. On the left, we see the results of multi-body dynamics analysis, assuming that no deformation occurred in the component due to force. On the right, the results reflect multi-flexible body dynamics, assuming that deformation can occur in the clutch. As demonstrated here, technology classifications depend on the physical phenomena or the application method we aim to analyze in a mechanical system. What you are watching is a clip of an arrow in flight after being released from the bowstring. While archery is a sport today, the bow has been one of the most fundamental long-range weapons operated by individuals since ancient times. What if we applied dynamic analysis to the movement of an arrow leaving the bow and flying toward the target? In the videos on the left and below, you can see how the hand draws a bowstring, causing the bow and string to bend under the force applied. The arrow is launched towards the target by the force of the bow as it tries to return to its original shape. The arrow flies due to the force exerted by string, and these videos show the results of analyzing this process using a dynamics model. The key is to define and analyze the physical properties of the bow and string, which deform under force, as well as the contact point between the hand and the string, and between the arrow and the target. In the top right video, we see the application of a dynamics analysis to a traditional Korean bow. It demonstrates the process of stringing a tightly curved bow and drawing the arrow. To quickly determine the deformation of the bow when the string is attached, static analysis has been applied, solving the equations of motion at a static position. The video you are watching features a trebuchet, a powerful, long-range weapon often seen in films set medieval Europe. This device throws heavy projectiles like stones to attack fortified castles from a distance. It effectively employs various physical principles, such as the rebel principle governed by kinematic constraints, the movement of weights, and the resulting action and reaction forces. These laws of physics make it an effective weapon for striking enemies safely from a distance. The video you're watching presents the results of applying dynamics analysis to a trebuchet. The weight of the projectile is influenced by gravity and the potential energy generated from its fall. The trebuchet, utilizing the principles of leverage, harnesses the energy to launch the projectile over long distances. Additionally, sophisticated contact algorithms are applied to analyze the bag containing the projectile and the part with the rope hanging from it. In modern times, the bow and arrow have been replaced by rifle as the most important personal firearm. What kind of dynamic analysis can be applied here? One of the most critical mechanisms in a rifle is a device that ensures the smooth feeding of the rounds from the magazine to the fire position. To model this component, it is essential to employ contact analysis as well as to define and analyze the forces acting on key parts such as the springs. These are crucial for accurately simulating the functionality of the system. As you can see, dynamic analysis allows you to verify whether the components within the rifle operate smoothly and to ensure that no excessive forces are generated that might cause damages to the parts. Wouldn't the trebuchet we looked at earlier be similar to modern missiles in that they hit a target from a distance? Unlike a trebuchet, which are used to target visible enemies within a certain range, missiles are precisely guided to reach and strike enemies far beyond the visual range. Now, let's apply dynamic analysis to missiles. First, the key consideration is how to define the lift acting on the missile's wings and the thrust that propels it forward. Then, we test the algorithm that controls the missile with a completed missile dynamics model. In this video, the lift acting on the missile's wings is modeled to be determined by the missile's orientation. This model was simulated using an algorithm that controls both the thrust magnitude and the orientation, allowing the missile to follow the desired trajectory. The video you see is a missile model that models the lift acting on the wings by considering the orientation of the missile. And it was simulated with an algorithm to control the magnitude of the thrust and the orientation to make the missile follow the desired trajectory. It defines and analyzes the missile model to link the magnitude and altitude of the thrust with a control algorithm to follow desired trajectory. As you can see, immediately after launch, the missile initially descends due to gravity, but then regains its original altitude as lift is generated by its deployed wings. In the video, the large arrow on the missile body indicates the direction of the thrust calculated by the missile control algorithm embedded with the dynamic model. By embedding the control algorithms into dynamic analysis models, the performance of the control algorithm can be verified at the design stage without testing the actual missile. We have briefly looked into the concepts of MBD, MFBD, contact, and control technologies by examining examples of dynamic analysis applied to essential weapons from the past and present, including bows, trebuchet, rifles, and missiles. Next, I'll explain how dynamic analysis is utilized within the defense industry across different categories and how it can be applied in various ways. The video you're watching is titled "What Robots Will Be Deployed in Future Worlds" and features a quadrupedal robot. Drones, wearable robots, quadrupedal walking robots, etc. are mechanical devices to minimize the input of manpower and equipment that people can wear directly. There is a growing demand for such robot systems that can perform their intended activities without loss of manpower on the battlefield for dangers by controlling mechanical systems from a distance or through artificial intelligence through various sensors and controls. Robots must have mechanical systems that can move autonomously according to their intended purposes, and they must also have systems that control their movements to perform the desired tasks. Mechanical systems can be defined as dynamic models by applying dynamic analysis technology and integrating control systems into them. Tests on robots and control systems can be conducted without creating actual robots. This video demonstrates the results of a dynamic analysis conducted to design a mechanical system that can replicate the walking motion of a horse, ensuring that the desired movement is accurately performed. To control a walking robot, it is essential to determine how each joint should move, the amount of force required, and how to control these movements. A dynamic model allows you to assess these aspects effectively. We can analyze and refine the control algorithm without creating a physical model by integrating the completed dynamic model with a control system. This enables the evaluation and improvement of systems in a virtual environment. This video is about a bipedal walking robot that requires more complex control than a quadrupedal walking system. In this case, Dynamic analysis can also be applied to perform a detailed assessment. Let's look at a slightly more complex mechanism. What you are watching is a model of a stem beast using Janssen linkage. This is a walking robot model that employs a 6-bar linkage to create a very smooth walking motion. Although it is possible to mathematically calculate the shape, angles, and length of links, here it has been implemented through dynamic analysis. In this way, a dynamic analysis model that implements a robot system with a mechanical mechanism on a computer allows you to evaluate the dynamic performance of a robot without creating an actual model. Dynamic analysis can be applied not only to walking robots but also to robotic systems designed for specialized tasks. This robot uses parallel connected arms to quickly move target objects from one specified position to another. Through the integration of dynamic modeling and control, the robot's movement is optimized to achieve a smoother and more efficient performance. The next example demonstrates the use of dynamic analysis in creating a digital twin. A digital twin involves replicating a real-world system within a virtual environment on a computer. Here is a digital twin of a real robot system and its control system that guides the robot along a specified trajectory. This digital twin replicates any errors occurring in the actual robot, allowing you to observe these issues virtually as they would appear in the physical system. Tests can be conducted under a wide range of virtual environments and conditions by utilizing a digital twin model. This approach allows you to identify and prevent potential issues in the actual system before they occur. This video demonstrates a dynamic analysis model of a drone created in a virtual environment that can be controlled using an actual joystick without creating an actual mechanical system. This approach allows you to develop a system that creates a virtual dynamic model of equipment used on a battlefield, enabling operators to learn how to operate the equipment effectively through joystick control in a simulated environment. We have explored the dynamic analysis used in the design of robots that can operate autonomously or to be controlled remotely without human intervention. Then, what are some dynamic analysis technologies related to humans? The footage you see now illustrates the calculations derived from dynamic modeling and analysis, which determine the loads acting on the joints of a wearable robot as a human performs specific movements. An important aspect is how we can model human movements, which differ from those of mechanical systems. Although collaboration with specialized research institutes, we could define and analyze the actual movements of the human body using dynamic models. We also apply technologies that integrate with the control systems to effectively analyze and manage the required power. In combat scenarios, equipment operated directly by personnel can expose the human body to significant external forces, potentially leading to severe accidents. The footage you are watching illustrates a dynamic analysis model that predicts the force exerted on the human body when operating an excavator. By understanding these forces, we can contribute to safer operations of heavy machinery in high-speed and high-weight environments typically found on the battlefield. Now that we've talked about the equipment used in combat environments, Let's discuss dynamic analysis applicable to vehicles operating on the battlefield. Vehicles used on battlefields navigate through rough off-road terrains with many bumps and obstacles. Dynamic analysis for such vehicles focuses on defining these irregular surfaces and assessing how the tire interact with these challenging conditions. This allows you to evaluate the performance of the suspension systems designed for these vehicles and ensure they meet the operational requirements needed for battlefield conditions. Certain vehicle components can undergo permanent deformation or damage if subjected to excessive force. Therefore, it is crucial to assess the level of external forces and the resulting stress in specific driving conditions, which can be achieved through dynamic analysis models. As shown in this video, we have analyzed the stress occurring in the suspension knuckle body while controlling the vehicle's direction during driving. This approach enables you to predict and evaluate the durability of critical components under real-world conditions. The manufactured vehicle must go through a process of evaluating and improving the vehicle's characteristics through driving tests on various road surfaces. Since testing a vehicle on an actual road requires considerable time and cost, the actual road surface is measured and converted into data, and the tests are conducted in a virtual environment. On the left, you can see a simulator that uses real vehicle data to input road surface measurements for all four wheels, allowing you to evaluate the vehicle's performance. On the right, there is a digital twin model of the simulator within a virtual environment. This digital twin has been adapted for developing and testing combat vehicles, replicating the same vehicle setup as seen on the left. As demonstrated in the video, we can observe similar wheel movements across both the systems, even when using identical road surface data. While having measurement data for each of the four wheels would be ideal, it is often unavailable. Therefore, an analysis technology that can inversely derive the movement applied to each wheel from the actual driving result is required. This is called TSG, Time Signal Generator. This calculates the movement of the wheels inversely from the actual measurement data through frequency analysis. By using this technology, a wider range of measurement data can be utilized for vehicle testing. You see a Humvee with front tires shaped like triangles. Rather than the tire rotating, a wrapped track belt turns to propel the vehicle forward. As it drives, the triangular tire transforms into a circular shape and the entire tire rotates. On well-paved roads, the vehicle moves with a circular wheel shape. However, when the terrain becomes rough or challenging for standard tires, the tires transform into triangular shapes and a track belt replaces the tires for movement. Can dynamic analysis technology be applied to such systems? On the right, you can see a reconfigurable wheel system. On the left, it is defined as a dynamic model. The wheel is equipped with a track belt instead of a traditional tire, allowing it to shift smoothly from a triangular shape to a circular shape and back, maintaining consistent ground contact and providing traction. The reconfigurable wheel system consists of two key mechanisms. This mechanism, which shifts the wheel shape from a triangle to a circle and back, and the power transmission mechanism, which moves the track to transmit power. The dynamic model is also designed to model both the mechanisms, so that it can be tested both during the shape change and the driving phase. In addition, the most essential analysis technology for this model involves modeling and analyzing the track, which consists of connected small track segments. The dynamic analysis model for the track system constructs the entire system by linking numerous small track bodies with the force elements. These individual track bodies move between the wheel components and the ground, transmitting power as they move. Let's take a closer look at some examples of applied track systems. Among the robotic systems mentioned earlier, we have a reconnaissance robot with a track system designed to carry out missions across various terrain environments. This is a representative example of a combat vehicle that applies a track system, a tank. Similar to Humvee, which we previously examined as it navigates off-road terrains, tanks operating in rugged environments can have their terrain profiles defined freely for testing within the dynamic model. An important aspect of operating tracked vehicles is ensuring the track maintains consistent tension during movement to prevent it from slipping off. We can study what should be considered to maintain this tension through a dynamic analysis model. The most important part of a track vehicle dynamic analysis is how quickly and accurately the track assemblies with many degrees of freedom can be analyzed. In this regard, RecurDyn has the most exceptional technologies. This video demonstrates various driving tests of armored vehicles and tanks analyzed using RecurDyn's track dynamic analysis. Various tests such as acceleration of tracked vehicles, passing over vertical obstacles, rapid deceleration, and driving on slope can be performed through dynamic analysis. Let's take a look at the examples of tests related to tracks conducted through dynamic analysis. The two videos at the top demonstrate the testing of rubber track characteristics. You can model the track assembly using CAD geometry of the track body and compare the dynamic analysis results with the physical test results. In the case of a rubber track, you can conduct simulations after converting the entire track assembly or the sprocket or wheel to flexible bodies. The video you're watching is not a combat vehicle, but it is an example of a technology that can be used for analyzing tracked vehicle dynamics. When the road surface is composed of small objects such as gravel, the tracked vehicle leaves a track-shaped mark on the road surface as it drives. Depending on the shape of the gravel that makes up the road surface and the shape of the track, the force is transmitted to the road surface as the vehicle drives in various ways. To analyze this phenomenon, you can apply DM technology, which refers to discrete element method, which allows you to simulate the interaction between the tracked vehicles and the gravel surface as shown in the video. The video illustrates a simulation of a tracked vehicle navigating a gravel road using the co-simulation of two programs, EDEM, which specializes in such analysis, and RecurDyn, which focuses on dynamic analysis for tracked vehicles. With this method, you can also simulate tracked vehicles moving over sand or gravel surfaces. As seen previously, depending on the track shape of the track system, the contact characteristics with the sprocket wheels that make up the system and the contact with the road surface will vary. In addition, by applying dynamic analysis technology, tracks of various shapes can be moved and the contact occurring with each part can be tested. Among the equipment operated on the battlefield, many consist of continuous bodies similar to tracks. Continuous bodies such as anchor chains for ships, winches, guide chains that protect the cables, and equipment that moves by contact can be tested by applying dynamic analysis. Until now, we've focused on systems operated on land. But now, let's shift our attention to the sky and space. What you're seeing here is footage of a solar panel that was compactly stored, being deployed widely in space. You can see the roll-up tube, which is a flat plate that was rolled up on the end mandrel of the solar panel and naturally rolled in the opposite direction to transform into a pillar shape that can support the left and right side of the panel. This is an example of an analysis performed using multi-flexible body dynamics analysis to check whether a mechanism using an elastic material that returns to original shape can implement the function that suits its purpose. The video on the bottom left demonstrates the changes in stress occurring in the roll-up tube during the solar panel's deployment process, as analyzed through dynamic analysis. The video on the right demonstrates the result of optimizing the controller that controls the up and down movement and rotation of the frame body on the left, so that the deployed solar panel can converge to the most stable position as quickly as possible. Likewise, dynamic analysis can be applied to develop military equipment operating in space. In space, where there is no gravity when satellite solar panels are deployed, movement occurs due to the inertia, which expands to the movement of the entire satellite, and energy must be consumed to control it. Therefore, it is necessary to design a controller that minimizes movement during deployment. This is an example of applying dynamic analysis and parameter optimization to select the optimized parameters for the controller that deploys the solar panel. We optimize the controller to control the rotation speed of each board joint so that the movement after deployment can be minimized at the fastest possible speed. Installing a heavy and precise piece of equipment like an aircraft engine onto a plane requires careful positional adjustments. Here, a winch capable of lifting heavy loads with minimal force is essential. The placement of the winch can determine the success of the operation. In addition, the design of the ideal guide rail shape is required considering the interference that may occur when moving the engine during the process. Unfortunately, we could not obtain the video from the company that performed this analysis. However, as shown in the figure, a dynamic analysis model can be created to consider the required movement path during engine assembly. Through this analysis, we can optimize the precise placement and orientation of the winch as well as the shape of the guide rail. The video you see here features a landing gear, one of the most representative mechanical systems in an aircraft. As you may have heard in recent news, incidents involving damage to aircraft tires and landing gears are common. The landing gear of an aircraft is subject to extremely high impact loads during takeoff and landing, which can lead to significant stress on the system. Therefore, it is crucial to ensure that the landing gear operates in a way that prevents dynamic loads from damaging any of the components within the system. Verifying this through dynamic analysis can help identify potential weaknesses and ensure the durability and safety of the landing gear under high impact conditions. The following is an example of an analysis of an aircraft carrier's landing wire using multi-flexible body dynamics analysis. Depending on the aircraft's speed and position, various external forces may be applied to the landing wire. You can analyze the situations that may occur at this time through dynamic analysis. The videos are dynamic analysis models defined for each purpose of analyzing the propeller drive mechanism of a helicopter. The first model focuses on how the propeller blade moves mechanically. The upper right model defines the propeller blade as a flexible model and focuses on the wing deflection and stress changes according to the same mechanism drive. The models below are analyzed models to verify the operating performance of a rotating propeller and the deformation of its blades. We have looked at equipment operated on land, sea, and air, and finally let's look at the case where the equipment is operated on the sea or water. For equipment operating on the water, a fundamental aspect of dynamic modeling is defining the buoyancy acting on the equipment as you see here. This is an example of applying the dynamic analysis model to analyze the degree of sinking under the water's surface. The load movement according to the operation of the equipment and the resulting buoyancy change depending on the shape of the equipment operated on water. The previous example simply illustrated the buoyancy acting on equipment operating on water. This time, let's look at an example of a dynamic analysis of both the movement of water itself and the movement of the equipment interacting with it. Unlike a traditional CFD, the fluid analysis technology that analyzes liquids as interactions between small fluid particles is called moving particle simulation, MPS. Applying this particle method to fluid analysis allows for dynamic interactions between fluids and moving equipment. The example you see demonstrates an analysis of the movement of water on the road surface using the MPS method, and the analysis of a driving car using dynamic analysis. The fluid behavior is analyzed using a fluid analysis program, while the vehicle behavior is analyzed using a multi-body dynamics program. This is an example of a co-simulation that simultaneously performs dynamics and fluid analysis to confirm how the fluid behavior penetrating a vehicle changes depending on the design of the vehicle's underbody as the vehicle drives on a waterway. In reality, many equipment on the battlefield must operate safely in submerged situations, and it is expected that applying this technology will greatly contribute to the design and improvement of combat equipment. The following example is a case of a tracked vehicle where the armored vehicle floats on the water and the track shoes act as paddles to move forward. At this time, the height of the water submerged by buoyancy and the propulsive force generated by the track can be confirmed through analysis. The driving performance and required conditions of a vehicle can be verified through dynamic analysis by the interaction between the fluid and armored vehicle dynamics models. Lastly, I've listed case studies to assist you further in applying dynamic analysis. This list includes our customers' cases and presentations from user conferences where dynamic analysis have been applied in this defense industry. Some materials can be downloaded from the Function Bay Technical Support site. This is a list of papers. As you can see, Various studies are being conducted using RecurDyn in the defense industry. These papers provide valuable insights into the application of dynamic analysis technologies in this critical field. You can see more of them here. Today, we explore the application of dynamic analysis in the defense industry, focusing on how this multi-body dynamics technology can be utilized through various case studies. While there are many other areas and equipment within the defense sector where dynamic analysis can be applied, I hope that the examples we discussed have provided you with some insights and assistance in applying this technology in your work. This is the end of this seminar, and I hope that it was helpful for you. If you have any questions about the content introduced today, or are interested in trying out the trial version of RecurDyn, please feel free to reach out through the Function Bay website. Thank you all for your attention and participation. See you next time. Thank you for being with us today. I hope the ideas and case studies we shared about multi-body dynamics in the defense industry will help you in your projects. If you do like the presentation materials or replay of the session, just fill out the short survey using the QR code on your screen. Your feedback is valuable to us, and it helps us make future webinars even better. We look forward to seeing you next time. Thank you again for your interest and participation.